So let's talk about simulations, or the first steps into the world of simulations, because in this video we'll not actually do simulations, but we will get kind of an idea about the nature of simulations. And the simulations in Houdini are called DOPs, or dynamic operators. And we can create a DOP network on the object level, but I would definitely not recommend doing that. What we will do is we still work on the SOP level, so we work inside of a geometry, and here you can create a DOP network as well. And then you can see that you did it right, so to say, because it has 4 inputs. Again, some shelf tools create DOP networks on the object level. Personally, I would never do that. I find it has only disadvantages and no advantage. So from now on, we will always create our DOP networks on the SOP level. So in the DOP network is where the simulations live. And we talked about the solver before, because a DOP network is a solver by itself. And mainly what this means is that every frame is dependent on the frame before, and we have a memory of things that change. So not every frame stands for itself. So usually we have some kind of input into a DOP network, but we can ignore this for now. Let's go in. And this now you can see is the dynamics environment, and this is DOPs. So every DOP network is built of at least 3 elements, and that is the solver, the object, and the source. I mean, the source is actually optional, but very often we have a source. It's good to remember it this way. So this chapter we talk about pops or particles, and this is why I want to show you the logic with pops. So if I type in pop, there are all kinds of nodes, and what we're looking for is the pop solver in the middle, then the pop object, and the pop source. There you go. So the way this is usually connected is the pop object goes to the left of the pop solver goes to the output, and then the pop source goes into the right input. So what this means is the pop object is where the points will end up in. The pop solver is the brain. So here is where the pop calculation happens. And if you go really close, you can see actually that there is a little brain on the node, which tells you that this is the thinker here. And then the pop source is where new points come in if you want that. Now, this is the basic setup, and we will see that many times in the next couple of videos. One thing you have to understand is this is not behaving like a SOP network. So it's not like everything comes from one direction and goes down, but this is more like a blueprint of explaining the world your simulation is happening in. So it's an explanation of everything that is involved. And the best way to explain that is by bringing in the gravity force, because currently we don't have any forces, and the gravity force you would connect here. So if DOP solver would work like a SOP network, then this wouldn't make any sense, because here the pop solver is where the calculation happens, and afterwards there's gravity. That doesn't make sense. So here you can see that it works a little bit different. It's its own way of thinking, and also you don't need the output flag anymore. The orange flag here just defines the end or the output of the simulation. Everything that is plugged in will be calculated. Be really careful that you not accidentally set this, because currently there would be no calculation if you set it to pop source, because the pop solver is not involved anymore. So make sure that your output flag is always on the output node, so that everything else is calculated. And what this basically describes is this is the kind of the God that calculates everything, and then all the other informations go into the network. And here's another thing that is different to the SOP world. The geometry spreadsheet looks different. So before, when we go outside, you can see there, long lists of numbers, as we know, of showing all the attributes. But when you inside of a DOP network, or actually you have selected a DOP network, you can see that your geometry spreadsheet looks different. And this now not necessarily only gives you the attributes of a certain geometry, but it gives you certain relationships. You can, for example, now see that the pop object is there, and it has different forces that are applied to it. For example, the gravity force. So this force here is applied to the pop object 1. And here you can again see that this is more like a blueprint of the world we live in. So we'll talk about this later, but just keep in mind, this is not just a bunch of numbers anymore, but this actually shows complex relationships and constraints between each other. So now, of course, a pop solver and a pop object and pop source are needed for a pop simulation. Likewise, there are a Vellum solver together with a Vellum object. Then there is a rigid body solver, and with that comes an RBD object, in this case actually a packed object. We will talk about this later, of course. Then there is a flip solver. With that comes a flip object. And finally there's a pyro solver, and with Houdini 18 it's actually a sparse pyro solver, and for that we need a smoke object, actually in this case a sparse smoke object. So you can see it's always the same logic, just with different kind of brains that calculate differently. So let's have a look at the different types of simulations there are in Houdini. So the first simulation we look at now in the next couple of videos is POPs, or particle operators. So the OP always stands for operator, and P in this case stands for particles, and that also includes pop grains. So POPs is actually very, very important, because all the nodes we learn in POPs we can use in almost all the other simulations with one exception. So, and we will, and this is actually super powerful because it teaches you the core mechanics of Houdini simulations. And what you can do with POPs, for example, is rain or sand or even snow. And especially with pop grains, you can make it kind of stick together and all kinds of stuff. So particles are super important. What we look at afterwards, and by the way, the order of those things is not random. I found a certain logic for myself where I feel like it makes the most sense to learn it, because every step it gets more complex and it teaches you something for the next topic. So, you know, people always discuss what the best order is. This is, in my opinion, the best order. So Vellum is the next one, is relatively new, only about 2 years old. And Vellum is soft bodies or soft geometries. So for example, cloth, and also cables and wires and stuff like that, but also soft bodies. So objects by itself that are, you know, kind of squishy or soft. And this replaces a couple of actual simulations. We'll talk about this, but one that is quite prominent still on the internet is FEMs. So if you see FEM, just keep in mind this is soft bodies that are now usually, at least for beginners, done with Vellum. Okay, so then we have RBDs, that is hard rigid body objects. So this is your classical destruction. So hard geometry that just breaks apart. One thing that is interesting is that RBDs, to kind of speed up the whole process, are actually calculated in form of points, in form of packed points. So again, even though it doesn't seem like it, understanding POPs is actually really valuable to understand RBDs. And in Vellum, you learn something very important, that is constraints, that we will then use in RBDs. And RBDs are surprisingly complex. So I think it makes sense to learn simpler stuff first and kind of ease into the simulation stuff before you jump to RBDs. After RBDs, we look at flips. And here is where it starts to become really slow and really big and complex. And flip is fluid simulations. And the interesting thing with fluid simulations is that they are partly points and partly volumes, but the point part is important because everything you learn in POPs you can reuse here. And then finally there's Pyro, which is the most complex part of Houdini. And it's mostly based, the simulation at least, is based on volumes, but with Houdini 18, a lot of it is outsourced into point simulations again. So again, we need to understand how to work with points. So as you can see, points are very important. One thing I want to point out, that RBDs, but especially flips and Pyro, even for advanced FXTDs, it's not an easy plug and play kind of thing. It's quite complex even for more experienced users. So that's why we also start with POPs and Vellum, because it's much easier to get into the whole thing before we go to the really complex stuff. But you will see what I'm talking about soon enough. So, and then finally, one thing that is not covered, I mean, there are a couple of things I think that are not covered, but the most important things are crowds and hair and fur. But especially the last one, actually hair and fur is pretty much a Vellum simulation. It's more like there is a specific workflow how to apply fur and all that we will not talk about. But hair nowadays is actually at least optional. also calculated with vellum. So it's not so much the simulation part that is special with hair and fur, but more the whole setup. So this is something that I decided is too specific, but the good news is once you went through the course, then crowds and hair and fur will be very easy for you to learn because you have such a wide understanding about the concepts that this will be relatively straightforward for you to research yourself. So, okay, this is just an overview about the different simulation types. And of course, we will talk about this in much more depth in the next couple of videos. So for now, hope this was helpful. Thank you very much.